he did not win Junior Olympics.
Your son?
Yeah.
For fencing?
That's cool. Are you his coach?
He practices 100 in the country, which is good for him. And there's potential for him to do more. So it's good. That's fantastic.
Can you go to college for fencing?
Only to the good colleges. Only to
Like Ivy League?
like Princeton,
Yeah.
Harvard, Stanford, USC. All right, new topic. Carbonyls. Carbonyls contain a carbon to oxygen double bond. And there's lots and lots of variation. We have two main families, just the regular carbonyls, and then things that are carboxyl. We're going to replace that N with an X. These are substituted carbonyls that have a second functional group. In terms of just pure regular carbonyls, we have two types, aldehydes and ketones. Now, it isn't immediately obvious why we need two completely different naming systems for these. That eventually reveals itself at the end of the course. Actually, we'll start it today. We'll go look at that. But its importance doesn't get revealed until later on. Okay, oxygen always makes two bonds. So oxygen has just made its two bonds right there. We'll have two lone pairs of electrons, and that leaves this carbon to make two bonds to something else. What's going to be the hybridization on that carbon?
SP2.
That's an SP2 trigonal planar. We have an SP2 trigonal planar group, and it's a carbon and an oxygen with a sigma bond, and then a pi bond on top of it. So this is an area of high electron density and lone pairs of electrons on the oxygen, making it capable of doing two types of reaction. The nucleophile could be the lone pair of electrons. Your nucleophile could be the electrons in the pi bond. Okay. I have a pi cloud, and I have two lone pairs of electrons, which means there are going to be choices. Here's something else. That bond is polar. Oxygen is the electronegative atom in this bond, and we'll be pulling electrons this way, which means this oxygen is a little bit hot, and this carbon is a little bit cold. So, if I react this molecule with electrophiles, I have to make a choice. Am I going to use the lone pair of electrons? Am I going to use these pi electrons? If I react it with acid, lone pair of electrons. If I react it with nucleophiles, then the nucleophiles are going to attack that carbon. Okay. So I have two types. This and that. They're both sp2, they're both trigonal planar. Only one of them has a hydrogen attached to the carbonyl. The carbonyl means this part right here, the carbon to oxygen double bond. That's my carbonyl functional group. These are called aldehydes, and these are called ketones. And they are so completely alike that it doesn't seem like there should be a need for any kind of demarcation between them. But there is a difference, because this has a hydrogen, and the loss of bonds to hydrogen and the gain of bonds to oxygen is oxidation. And the aldehyde can do an oxidation reaction that a ketone is incapable of doing. And that reaction is of biological significance. And so we're not going to pretend that these two are completely the same. They are different enough that they get different naming systems. All right, so the naming system has to include the carbon. And for an aldehyde, this is easy because the functional group is terminal. So I name whatever my group for the R is, and then add 1 to it, so that it includes this. And just the way that alcohols were ethanol, propanol, butanol, the aldehydes get to be propanal, butanal, pentanal. You name whatever that R group is, you include this carbon. Yeah, I know there's a joke on the book. See if you can spot. So use the less to spot it. So basically what this is, just right here, is the longest chain. Ketones, you have to name, this is now your chain. So let's have this be R and this be R prime. This is R plus R prime plus the carbon in the middle. And own. So R plus R prime plus 1 basically is just the longest chain. Aldehydes don't need a numbering system. Ketones are going to need a numbered position. Okay. Let's go next. name these. It's a representative set of molecules. All right. First, identify which family does this belong to. Is this a ketone or an aldehyde? It's an aldehyde. How many total carbons does it have? 2. And the word for 2 carbons is F. So this gets to be ethanal. Which family does this belong to? Is this a ketone or an aldehyde? That's a ketone. And its total number of carbons in the chain is 4, and the chemical prefix for 4 is but. So this is butanone. If you call up the chemical manufacturer and say, I would like 10 liters of butanone, please, they say to you, sure, okay. But I just told you I needed a numbering system for this. What number is this butanone? Doesn't have a number, doesn't need one. It is 2 butanone, but is there such a thing as 3 butanone? This would be 3 butanone. 3 butanone is 2 butanone. Would there be such a thing as 1 butanone? No, can't be at the 1. To be at the terminal carbon of the chain would mean it's no longer a ketone. Ketones have carbons on both sides of the carbonyl. So there is no 1, but somebody has soaked and washed all of the dry erasers in the building. Which is great because they clean really nicely now, except the board is now wet. So it's just butanone. If you write the 2 in, it's fine. Go ahead, write the 2 in. It's good practice. What about this one? It's a ketone.
Oh, there's 6. 2 hexes, no. 3 hexes.
Don't feel the need to read them from left to right. There is no convention that says you read the molecules from left to right, top to bottom. 1, 2, 3, 4, 5, 6 carbons in the chain with the carbonyl at carbon number 4, unless I read it this way. 1, 2, 3. 3 is smaller than 4. Therefore, it is the most efficient naming system. That's cyclohexanone. What numbered carbon is the ketone at? That's a 1. So I don't need to write it down. Is there ever a time when I would need to write down the number for a cycloketone? How about now? What is it now?
3 methyl cyclohexanone.
That methyl is at the 3. The ketone gets to be carbon number 1 because it has 2 bonds, and those bonds are to an oxygen. And oxygen is more important than carbon because it's further to the right on the periodic table, and it does more stuff. This is clearly the functional group. 2 and 3, 4, 5, 6. And the methyl. Ooh, is that the trans or the cis? The correct answer to my question is no. My question was, is this the trans or the cis? No. No, it's not. Why is it not?
It's flat.
This is flat. Cis or trans means different side of the ring, same side of the ring. This is flat. It is not on either face of the ring. It is slap dab in the middle. So this is just free. Excellent. Last one. How many carbons does it have? How many carbons in the longest chain? And what is the prefix for 1 carbon? It's methanal. Methanal goes by a widely observed trivial name. All of these on the board are currently the systematic names. This has a trivial name that everybody knows. Nobody?
Let's start with
F.
Good job,
I didn't even tell you what we do with formaldehyde. What do we do with formaldehyde? Get people with it, get things with it. You took your cigarettes. You sure? I'm going to have to edit that out of the video. Formaldehyde is a small chemical molecule that can be abused the same way that toluene was a nice small molecule that you can abuse it by inhaling, but it's a really, really dumb idea. Bad, 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 bad things happen to people who smoke sherm. Bad. I'm not even going to name it. I forgot how to spell it. Acetanilide. That's not even that. That's not even its name. I'm way off. We'll keep it as ethanol. All right. Form is from the Latin for ant, formica. Because ant bites are formic acid, which only has 1 carbon. And this is the aldehyde of that acid. All right, let's look at some reactions. Oh, I got a couple of cool, good ones. I love this one. Let's do these. Let's stretch the name just to a couple of, because there's one that we've already seen, And then there's a chemical that we're going to use in lab. So let's just get the naming of those out of the way. What's this? Benzaldehyde. There's two ketones that are aromatic, which you have to know the name of. I was going to tell you that ethanol is called acetaldehyde. I didn't bother. Acet. Ooh, here we go. Acet is this group. So the correct name is propanone, but everybody calls it acetone. So form is this. Actually, well, it's really the whole thing. And acet is this. And here's where we make a distinction between benz and fen. Benz is C6H5 and then a carbon. Benz is 7 carbons in size. Fen is 6 carbons in size. So this is a fen with an aceto group, one of them, and it's a ketone. There is a competing name that we're not going to use. Methyl ethyl ketone. You name what's on either side of the carbonyl and then name what classification it is. Methyl ethyl ketone. All right? Don't use that. But that's what this is. It's an acetone and a phenyl and a ketone. This is a 7 carbon molecule that is also an aldehyde. Benzophenone, which tells us that is a 7 carbon fragment and a 6 carbon fragment sewed together into a ketone. You're going to be using, well, you know that one already. You're going to be using this one in lab. All right, let's look at some reactions. See what we can figure out. Here is a nice small ketone, aldehyde is ethanol. see what it does. It has a positive end here. It has a negative end there. It has lone pairs and a pi cloud. What else have we got? Electrophilic additions, nucleophilic substitutions. I've got electrophilic additions. These are the mechanisms that I've seen so far. Any of those stand out as being likely candidates?
You wrote it twice.
Oh, I did. I did. This second one was supposed to be substitution. All right, so we've seen electrophilic addition across double bonds. If I had a double bond, I could add something positive and something negative to that double bond. Does that look like something that we might do here? Maybe. Should we rule it in, keep it in, or rule it out?
Keep it in.
We're going to leave it on. All right, nucleophilic substitution. Should I keep it on the board or can I rule it out?
Keep it.
Why am I keeping it? All right, let's back up. Why am I keeping electrophilic addition? And why do you think it's possible? Because there's a double bond. And we've seen electrophilic additions across a double bond. And so, although this is unfamiliar to me, it sounds, the reactant's got something similar. Okay, substitutions. Nucleophilic substitutions.
Oh, there's no leaving group.
There's no leaving group. It's not that. Eliminations.
No.
Why not?
Because it's isolated dyene, right?
Or
There's no leaving.
there's no leaving group. And then electrophilic substitution was what we did to benzene rings. This is going to be a substitution. Why not?
No leaving group.
Because there's no leaving group. That leaves me with electrophilic additions. But how many mechanisms are in the book? For eliminations. And then I have substitutions. I have two types of substitution. I've got the electrophilic and I've got the nucleophilic. We saw the nucleophilic. Haloalkanes do nucleophilic substitution, and benzene rings do electrophilic substitution. And then I have additions. And there are two types of additions. There's the electrophilic addition that happens to alkenes where both sides of the double bond are the same. That's a clue. In an electrophilic addition, it's a carbon-to-carbon double bond. Both sides of the double bond are the same. Both sides of that pi bond, both carbons. And then there is nucleophilic addition, which is the only remaining reaction that we haven't seen yet. If I had an electrophile, I could perhaps have this happen. Have that pi bond reach out and grab it. We've seen pi bonds do that before. I am not ruling it out. I could also, if that electrophile were friendly towards a lone pair of electrons, instead of being an electrophile, perhaps it were an acid, then I would really say, oh, I like that. I like this better. This is just acid-base. I kind of like that. And that goes along with everything that we've seen oxygen do up to this point. What has been the key to every single oxygen reaction that we've seen up to this point? Protonate the oxygen, because the oxygen, without it being protonated, is a terrible leaving group. And then I have the option to throw a nucleophile into the mix. What would a nucleophile do? Nucleophile sees this positive and goes and takes it. Did I mention this molecule is flat? When we saw nucleophilic substitutions, one of the things that we had to take into account was give the nucleophile enough space to do the reaction. Because being an acid and being a base is easy. That's on the it's always on the outside. Always on the outside. And hydrogens are always terminal. Unless you're in inorganic chemistry and you just learned that they're not. Hydrogens are always terminal. So if this E plus is an H plus, that's easy. That's what I'm going to end up doing here. But if I'm a nucleophile, I could go this way, or in fact, I could go that way. This molecule's flat. It's giving me a really good target for the nucleophile to see. But there is no leaving group, so it's not a nucleophilic substitution. It's going to be a nucleophilic addition. So ketones and aldehydes react by nucleophilic addition. There is some acid-base chemistry in there, and we are going to see it, and it's here. Okay? Anybody want to be a mortician? No. You're never going to go out of business. In all of the years, I've had one student that says, I really want to be a mortician. Do you know how much you charge to bury dead people?
A lot.
As much as you want, because who's going to say no? Grandma just died, right? Who knows how much it costs to embalm grandma, bury grandma, burn grandma, I don't know. But how much they charge you, and this has been well documented since the 1950s. There's a book called The Hidden Persuaders. It was written in the 50s or the 60s, which is about how marketing has a massive markup for products that you will not say no to. The casket costs $7,000. It cost them $25 to make it. But we dare you to say no to the $7,000 casket, because grandma deserves it. Yeah. Same for diamonds. We were talking about diamonds yesterday in inorganic. It's the same thing. The markup is ridiculous, and you will never be without business. I think that some of the I should stop. I think that there have been links to organized crime. So you might not just be able, oh, I'm going to open a mortuary. It might be a little, the market might be a little bit more protective than that. Okay. Pen die.
It's not that much. It's like brown. Like it's a lot. It's like not that much.
Let's look at some nucleophilic additions. All right. All I need is this. You can put whatever groups you want here. All I need is this. It doesn't matter what this is. What this nucleophile is immaterial. They're all going to do the same thing. So you can tell me what carbonyl it is that you want here. What carbonyl do you want? What should go here?
Methyl.
Who?
A methyl.
And here?
Hydrogen.
Okay. What nucleophile should we use?
OH.
Who?
OH.
I think I need to get my ears syringed.
I just need to talk
I'm
about it.
completely congested. Really, really bad. I'm hoping it's just the sebum. All right. Delta negative, delta positive. Is this molecule chiral? No, of course not. They have two bonds that are the same. How about now?
Yes.
The carbon that you attacked, because it was delta positive, is holding on to the oxygen twice. Once with a sigma bond, and we don't break the sigma bonds, and once with a pi bond. We break the pi bond. The electrons dead end onto that oxygen, leaving it negatively charged, at which point our nucleophilic addition is done. There is nowhere else to go. But I've left that oxygen hanging with a negative charge, and it needs to go away. So I need a part 2. Part 1 is performed in base, in sodium hydroxide. So you take your ethanol, you add some sodium hydroxide, you give it a stir, it makes this, and then when you're reading the procedure in the lab book says, adjust the pH until it's slightly acidic. And you just go ahead and you do it. You haven't asked yourself why. You adjust the pH back to being slightly acidic so that that negatively charged intermediate can now pick up hydrogen and go and be the finished product. This last step, we may have mentioned it already, is called acid workup. And we do acid workup after we use strong nucleophiles. In the presence of hydroxide, strong base, negatively charged, cannot have any positives in this part of the mechanism. There are no positives. It's in base. There are no positives in base. You only get positives in acid. So to make my negative go away, because it's stuck, there is no leaving group. There's no leaving group, so I cannot resolve the fact that this has a negative charge, and I now have to add acid. Is my product chiral?
No.
No. What is my product?
Ethodiol?
It's a diol. What type of diol is it? This is glycol, it's antifreeze, and it is 1,2-ethane diol. That is how we normally see diols, and this is what we would call a vicinal diol. What does vicinal mean? On adjacent carbons. Is my product a vicinal diol?
This one?
Mm-hmm. The product of this reaction by nucleophilic addition.
It's a geminal diol.
This is a geminal diol, and it is going to be that way every time we do the reaction, because all you do when you change the reaction around is you change the identity of these two groups. Is this now a propyl and this a phenyl? Okay, still made a geminal diol. So, ketone or aldehyde plus hydroxide makes a geminal diol. Is my product chiral? It's not chiral because I have two groups that are the same as each other. Can I invent a reaction that makes a chiral product? Let's try a little harder. Here's what I want. I want the product of this next reaction to be chiral. The mechanism's not going to change. There will be a step one. Step one is my nucleophile. And then there will be a step two. Step two is the acid workup. If I design the reaction correctly, I will guarantee that my product is chiral. Okay, let's go. What do I want here?
Methyl.
What do I want here?
Hydrogen. Methoxide.
Ooh. There you go. Is my product chiral? Yeah. 4 different groups, all singly bonded and therefore tetrahedral around a central carbon, means it has no rotational symmetry. None. It only has its own identity and therefore is chiral. Okay. Did I make the R or the S? My product, right there. Is that the R or the S? Can't tell. Can't tell, because it's not a Fisher projection and it's not in perspective. So I don't know if I'm viewing this molecule down the bond of the lowest priority because I never drew it that way. Do I make the R or the S? probably make both. I probably make both. Did I mention that this was flat? This is flat. Reaction could come from this side, or it could come from this side. Product is going to be racemic. It's going to be both the R and the S. There are times when it's not, but it's probably going to be racemic. If attacking on the top face makes the R isomer, then this is called the re face of the molecule. Attack addition at the re. This molecule is flat. It has two faces, one on the top, one on the bottom. The re face makes the R isomer. The C face makes the S isomer. You have two options. You can attack at the re or at the C. You could make the R or you could make the S. Chances are you're doing them both equally, and it doesn't matter. Okay, see you ready.
During this spot? Did you talk to him yesterday?
No.
Oh, you did? Just follow.
Who plays soccer? Do you have a new coach? His reputation has